She's the assistant professor at Duke Quantum Center at Duke University and jointly appointed as the principal investigator at that center. Please welcome to the stage, Huanqian Lo.
Okay, thanks, Wade, and I'm really excited to be here. I work with neutral atom arrays in optical tweezers, and each bright dot that you see on the screen over here actually corresponds to a single atom that we can actually control pristinely in my lab. And so today I'm very excited to share with everyone the why, the how, and the what the what and the how you can use these neutral atom arrays for quantum computing. Okay, so like all the other platforms that are used for quantum computing and simulation, tweezer arrays need to be able to provide control of qubits that are scalable and programmable. Right, so by tweezer arrays, I mean arrays of single atoms that you can actually trap in these reconfigurable tweezers, and each tweezer holds a single atom, which corresponds to one physical qubit. How do I generate these tweezers? Well, I simply send laser beams through this microscope objective over here, which brings them to a highly focused tight spot. But now you might say, okay, if I want 100 qubits, doesn't that mean that I need 100 different laser beams? That doesn't sound very scalable at all. Well, it turns out that instead of building 100 separate lasers, you can use these magical devices, like this acousto-optic deflector over here, which basically takes one single powerful laser beam and splits it into many smaller laser beams, each of which can be individually controlled. So here you see a picture of atoms fluorescing inside 400 optical tweezer traps. But now, you have to know that the loading of single atoms into these optical tweezer traps are highly probabilistic. So just because we have 400 traps doesn't mean that we have 400 single atoms. And in fact, if you look at a single shot image of these atoms, it's actually full of defects. Now, is it bad to have defects? As alluded to just now in the question and answer session, one of the earliest applications of these noisy intermediate scale quantum devices that we have today is quantum simulation. And by quantum simulation, I mean that we tackle the kinds of problems that currently take up a lot of resources in a classical supercomputer, like materials research problems or chemistry problems. But now, we have these clever theorists, like the other speakers of the session, Lex, who write down equations that model these complex phenomena, and instead of feeding them into a classical supercomputer, we basically mimic those equations using the neutral atoms that we have in our lab. The underlying assumption, though, is that we need to be able to control these neutral atoms very pristinely, which also assumes that we start off with a defect-free array. But now you might say, wait a minute, you just said that the loading of single atoms into these optical tweezers is probabilistic. So if you want to have a large defect-free array, it's a very challenging problem. It's almost like saying that I want to have 100 coins, and I hope that I can get 100 hits. What are the odds? That's terrible. Now we can play some tricks instead. Suppose I don't have 100 coins, but I have 200 coins. And I flip them, and I get roughly 100 hits. And I very quickly reshuffle them such that I have a defect-free array of 100 hits. Those are the tricks that we play over here with the second set of mobile optical tweezers that simply pick up those atoms and move them to the sites that we care about. So here you see actually successions of pairs of images. Right? The first one is full of defects, and the second one quickly rearranges them. How quickly? Faster than a blink of an eye, about tens of milliseconds or so. In fact, there was actually this defect-free rearrangement technology that was invented in 2016 that really enabled the field of neutral atom arrays to take off in the last decade or so. And so here you see a few different images of programmable geometries that we can achieve, right? Like the honeycomb, which is interesting for understanding graphene, or the buckyball 3D figure over there. Now, so far, all of these atoms that you see over here are all non-interacting. Okay? So in order to get them to interact with each other, we need to drive them to these highly excited states called Rydberg states. This is also how we actually entangle different atoms together that we later use for this quantum computer. Okay, so far I've talked about using these neutral atom arrays for understanding materials, for chemistry, but there's actually one very exciting frontier that these Rydberg atom arrays are particularly good at tackling, which is solving optimization problems. Okay, so suppose you are the director of a mobile phone company, and you want to determine where to place your antennas such that you can maximize coverage of your antennas, but minimize interference between them. Where would you place these antennas? Well, if you've got many possible locations to choose from, the optimal choice of this antenna placement is actually a very challenging problem. Right? It belongs to what we call an NP-complete problem, a non-deterministic polynomial time problem. Now, instead of solving this problem using brute force, turns out that Rydberg atom arrays actually offers a native hardware-efficient encoding of the solution to these kinds of problems. Loosely speaking, the idea is that we can actually arrange these atoms in arbitrary geometries to mimic the positions, the candidate positions that you have for these antennas. And then when we excite them to the Rydberg state, that strong interactions between them actually now mimics the minimization of interference between the atoms. And so solving these kinds of optimization problems have also other applications. For instance, figuring out how you might want to immunize a network against some virus that is spreading. OK, so far what we've covered is all analog quantum computing. But if you want to build actually a more powerful universal digital quantum computer, which is what we're ultimately after, you need to be able to have entangling gates that are very, very good between two atoms. So here you can see that actually in the last decade or so, there's really been tremendous progress in this neutral atom array community, where in the last 5 years, for instance, you see the gate fidelity, the 2-qubit gate fidelity, go up by almost an order of magnitude. And impressively, the community has demonstrated that you can actually have these high-fidelity gates between different pairs of qubits with up to 60 qubits in parallel. Remember those movable tweezers that you previously saw that we used to get this defect-free arrays? Now you see them again in a digital quantum processor, but they're actually used now to actually spread this entanglement through the entire array. So here you see, oops, OK. If you could play the video, please. Yeah, so here you see how you can use these movable tweezers to slide the atoms around and actually use this to generate the toric code, which is an important topological quantum error-correcting code. And finally, you might envision what such a neutral atom array quantum processor might look like. You can have different zones, right? Some zones used for storage, others for entanglement, and some for readout. And again, you use these movable tweezers to come in and slide the atoms between the different zones. And it was just demonstrated last year, for instance, by a group at Harvard and MIT, that you can have up to 48 logical qubits based on about 300 physical qubits or so. OK, so if there's only one message you could remember from this talk, it would be that neutral atom arrays are really a very fast-rising platform for quantum computing and simulation. The outlook is very bright. We have now demonstrated as a community up to 6,100 highly coherent qubits. There's also a big push towards making highly robust qubits, including here in North Carolina at the Duke Quantum Center. And there's really a lot of attention now from both academia and industry. That's all.
All right. I'm pretty sure atom-sized optical tweezers is how my grandma got her eyebrows to be just so thin. So thin. All right, if you have questions about what you've just seen, I have plenty of them, but I'm your host. Raise your hand. We'll come out there and allow you to ask them. Once again, Alicia, you found our first contestant.
Yes, thank you so much. That was very deep. What can you use it for? That's what I'm trying. What is the practical application for what you're talking about?
Right, so great question. The practical application for these optical tweezer arrays are basically using them to understand materials and chemistry. And one of the most difficult things about understanding materials, for instance, are their properties. Right? If you can get a microscopic picture of what it really looks like in a material, you could use that to understand how to engineer materials that have better conductivity and other properties that you desire.
All right, we got a question right over here in the front row.
Is the tweezer process entirely manual, and or can that be automated?
That's all automated.
All right, other questions, other questions. We've got one here in the center aisle, so I'll come back here to you. All right, what's your question?
Thanks. So you showed something that looks very interesting, two-dimensional. Can you talk a bit about how you make it three-dimensional? Because two-dimensional, I think, cannot scale as well as three-dimensional.
OK, so the question is about how you can make these tweezer arrays three-dimensional. So there are a few different ways to do them. That experiment that showed those images that had them, they actually used an electrically tunable lens, where basically you can use different voltages to tune the effective focus. That's one method.
All right, Alicia, who do we have over here?
Have you encountered a practical limit for the number of qubits you can implement this way?
Great question. So what limits the scalability of our platform? One of them is pretty much what is the field of view of the microscope objective that you're looking at, because you're limited in terms of, well, there's only so much space, and then you can only squeeze so many qubits in between with the tweezers. That's one of the limits. The others come in terms of the amount of laser power, right? I said that you could use these devices, but you must have a powerful laser to begin with to spread them out. Other things like the bandwidth of the devices and things like that.
Excellent. All right, we have a question here in the back. Find out some more information about potentially these tweezers. All right, sir.
My name is Pierre, we're for IBM. Can you talk about how this architecture differs from IBM's approach using gates rather than neural atom array?
Right, so in the end, they are both quantum devices, both the IBM superconducting qubits and also the neutral atoms. They are very different in the sense that the neutral atoms that we get, it's not something that we actually have to fabricate. We just get them coming out of an oven. Every atom is essentially identical. And then in the IBM case, well, it's really very heroic efforts in terms of really trying to make them very pristine and things like that. Yeah.
All right, folks, give it up for Huanqian Lo.